All right, so today we're going to continue our discussion on reflection. Okay, we have looked at reflection as a phenomena. Okay, so again, the word phenomena. Okay, phenomena is a natural occurrence, something that happens naturally that can be explained by science. For example, when the sun sets, why is it that sometimes it's yellow color? Why is it sometimes it's purple color? Why is it sometimes it's red color? All these are phenomena. Okay, natural, kejadian semula jadi, that can be explained using scientific concepts. Okay, so reflection is a phenomena where you have an incident angle going towards a reflector and it will be reflected back. And reflection follows the law of reflection, which says that the incident angle and the reflected angle, okay, must be the same value. Okay, and it is the same value when you measure it against a normal line. Okay, so this is the incident, this is the reflected, and this is the normal line. Okay, remember the normal line is always 90 degrees to the reflector. Okay, and so we find that the angle of incidence I must equal to the angle of reflection R. Okay, so we're going to begin our class today by looking at a few applications, okay, of reflections of waves in our daily life. So here is the first one. Okay, sorry. So one of the applications of reflection of waves, okay, happens in an echo. Okay, like we saw last week. We saw on Monday, if you shout inside a canyon and then suddenly you hear your voice back. Okay, it's not because there's somebody else on the other side that's shouting back at you, but it's because it is an echo. Okay, and so there are three types of sound waves, okay, that are within a range of frequency that is able to be reflected. Okay, first of all is the infrasonic waves. So infrasonic waves are waves that have less than 20 hertz. Okay, then there is normal audible sound, which is the sound that we can hear. Okay, the sound that we can hear. And this is about 20 to 20,000 hertz, 20 to 20 kilohertz. So this is sounds that we can hear, frequencies that we can hear. Remember, guys, frequency relates to how high pitch and how low pitch the sound is. Nothing to do with the volume. Okay, remember that volume only has to do with the amplitude of the waves. Okay, how high the waves is the volume. How many waves there are in 1 second is the frequency. Okay, so nothing to do with loud and soft. It's just, how high pitch and how low pitch it is. Okay, normal audio sound. For us, we can hear, okay, 20 to 20,000 hertz. Okay, now then after that, above the normal audio sound is what we call ultrasonic waves, or otherwise known as the ultrasound. Okay, if you ever work in a clinic before, or if you have any experience, with scanning, okay, you will hear that there's ultrasound. Okay, so ultrasound are sound that is above 20,000 hertz. Okay, and these are usually frequencies that usually dogs can hear. Dogs can hear beyond what humans can hear. We can hear up to 20,000 hertz. They can even hear higher pitches. That's why dog whistle, if you've ever had a dog whistle, when you blow on a dog whistle, how hard you blow also, okay, you cannot hear anything. Because the dog whistle is designed in such a way that when you blow the whistle, only the dogs can hear the whistle. Because the frequency is so high that our ears cannot catch it. Okay, it's pretty amazing when you think about it. Okay, that there are actually sounds that our ears cannot hear. Okay, sounds that are less than 20 hertz, which is very deep, okay, very low frequency, okay, or sounds that are beyond 20,000 hertz, okay, which is like super high pitch, okay, but the dog can hear it. Okay, and so let's take a look at an example of an echo. So we have this trumpeter over here, okay, that is playing his or her trumpet. Sorry, I don't know what is the designation for this person, but I'm just going to, sorry. All right, let's play this video. Okay. Okay, it looks like a her. Okay, it looks like a her. But the thing is this okay. Notice that, okay, of course she's also playing with a very high amplitude, a very loud volume. But notice that the frequency is getting higher and higher. Okay, again, now we have to disassociate, we have to separate frequency and amplitude. She is playing with a high volume, correct? But she's also getting higher and higher frequency. She's trying to hit that high frequency, and we can still hear it now. If we can still hear it now, means that it hasn't even reached 20,000 hertz yet. Okay, it hasn't reached 20,000 hertz yet. Okay, this next example, I don't think it's a, yeah, I don't think this is a this one. But anyway, if, oh, there is. Okay, so you hear the echo going all around. So you hear like, sorry. Okay, so if you ever walk in a tunnel, you will definitely experience this. Okay, you hear, but it's not bouncing back at you. It's kind of bouncing all over the place. Whereas just now, in the case of the trumpeter, she was playing towards a wall and then the wall just bounced it back at her. And there's a slight time gap over there. Do you notice that? Like it's not immediately she play and then immediately she hear the echo. There's a small time lapse over there. Okay, there's a small time gap over there. So that shows that when the waves travel and come back, it takes some time, okay, for the waves to return back to you. Okay, and this becomes very important later when we do our calculation question. Okay, this next example, I highly recommend, I highly recommend that you listen to this with your earphones. Okay, but if in any case, you find that you cannot tahan atau kamu rasa kamu akan sangat kegelian, okay, I would suggest that you start reducing the volume or you just take off the earphones Okay, okay, I can't take this anymore. Okay, it's a 3-minute video, and I want you to, okay, what I'm going to do is I'm going to play frequencies with the same amplitude. Everything has the same amplitude, but they just have different frequencies. I want you to tell me, or at least detect I want you to tell me, when did you start hearing the sound? Okay, so 20 hertz is what we are supposed to be able to hear okay, but some people like me who are very old already, I can't hear 20 hertz It's too small of a sound for me. Okay, too small of a frequency to me. So put on your earphones or your headphones, okay, and listen to this signal. It's going to just produce one only okay, at different frequencies. Okay, low frequency means very deep sound. High frequency means high, very high pitch You will find that as we go to a bigger frequency, okay, what is going to happen is that you are going to start to feel very girly But okay, just try to endure it. But jangan sampai kopi telinga pecah Okay, no it won't pecah. It just make sure you don't tahan. Okay, so take note of when you were able to hear the sound and when you could not hear the sound anymore. Okay, we should be able to hear the sounds from here, but I'm not sure whether you can hear. Okay, notice that the frequency is just going to get higher and higher. Okay. Okay, so when were you able to start hearing and when did you stop hearing the sound? I started hearing about 100 hertz. Okay, for me lah. I started hearing about 100. Type your answers in the chat lah. When did you hear the sound and when did you stop hearing the sound? I started hearing about 100 hertz and I stopped hearing anything about 15,000 hertz, which is pretty normal for an old guy like me lah. So you should be able to hear a little bit lower and a little bit higher than mine. Were you able to hear anything at all? Okay, but anyway, the first thing that I want you to notice, okay, if you want to type, you can type your answer lah. 1,100 lah. Wow. Rahman, 9,920. Oh no. Oh, okay, you took off your earphone to 15,000 hertz. Wow, Joey, you have the same ears as me. How come? You should be able to hear better than me. Oh no, Rahman. Wong Yik's one, 140 to 12,000. Am I the only one that do I have super hearing? I stopped hearing at about 50. Okay, Ira is not too bad lah. 18,000. Yeah. People like you at your age, you should be able to hear up to about 18 or 19. Definitely better than me. Mine is about 15,000. I stopped hearing now. Ethan, see, even better. Ethan is the ultimate youngster lah. 110 to this one. But Rahman, sampai 9,000 sejak. Okay, and you start at 16,000. Yeah, I think at your age, at 16 years old, you should be able to hear a higher frequency than me. Okay, one thing I want you to notice is that actually, if you had not taken off your earphones, I know it's very girly, it's very girly to hear. It's very girly to hear, and the tendency to take off the earphone is very high lah. Okay, but actually, what is happening is that all the sounds since the very beginning have been at the same amplitude. The volume has never changed. The only thing that has changed is the frequency. And our brain tricks us into thinking that higher frequency means higher volume. And so we, our response is, okay, kita mau tutup telinga sebab we cannot tahan because we think it is a very loud sound and we think that our ears cannot taking. Oh, your computer is lagging. Okay, don't worry. Okay, we think that our ears cannot take that higher frequency. Actually, it can. Okay, it's just our eardrums are just going to vibrate at a certain frequency, but it's not going to be smashed because the amplitude, the volume is actually the same. I have not changed the volume at all. Okay, it's just that when we hear high-pitched sound, our brain tricks us into thinking, oh, okay, high-pitched sound is dangerous. Okay, actually, what you should have, if any one of you have dogs, right? What you should do is you should try to play this. You should try to play this. Actually, this YouTube video, okay, this YouTube video, which is so aptly named admin of this site, okay, this YouTube video plays beyond 20,000. Okay, and what you should do is you should play this sound. If you have dogs in your house, you should play this sound for your dogs to hear. You'll find at higher frequencies, certain dogs and cats, they will start to pay attention at higher frequencies. At the low frequency, they're like, okay, whatever, I can't really hear it. But at higher frequencies, they will start to tilt their head, which is what happened with my dogs just now. They started tilting their head about 12,000 hertz. Okay, they are wondering, why am I not doing anything now? So they started tilting their heads, wondering what is that sound coming from now. Okay, and if you play at higher frequencies, they will be able to hear one. Okay, it's pretty interesting now. Okay, go and check this out. Okay, and if you want to test your ears again, okay, if you want to test your ears again, you can always go and watch this video. Very, very readily available at the in YouTube. Okay, and then see what you can see properly lah. Okay, now I know now we are using Google Meet, mungkin a little bit lag here and there. Go to the YouTube website. Okay, put on your earphones. Okay, maybe don't put it at such a high volume lah. Okay, just put it at the normal volume so that you don't have to feel very girly. Yeah, see how far you can actually hear. Okay, all right. This next one, another application of reflection of waves is the technology of hearing aids. Okay, so over here we have this cute baby, okay, who is finally hearing her mom speak for the first time now. She was born deaf, okay, and so they had to have a special, hearing aid for her. Okay, and so since she came out now, she has not heard the sound of her mom's voice. Okay, and this is her hearing for the first time now. Okay, sorry. No, it's a video. Okay, it's a video. Trigger warning or whatever that triggers you, okay, it's a warning.
Hello. Hello. I've never seen that face before. Hi. Are you emotional? You're gonna make me cry. Hi. Use your little chin. Hi. Yeah, are you gonna be emotional like your mama? Yeah. You're so sweet. Yeah. 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 I love you. I love you.
Okay, so
I love you.
so technology is such that we now use reflection of waves to help many people who are not able to hear again especially newborn babies Okay, it's pretty sad that some newborn babies they are born and they cannot hear anything at all, so they don't recognize any sounds. So the aid of the hearing aids okay, the hearing aids definitely help in getting babies especially to recognize sounds around them so that they can they can function better in life Some babies, they are born deaf but they're actually not mute. I think if you're deaf and mute, it's a little bit tougher But some babies are just born deaf, but they can actually speak. They can cry. They can, they can speak. So having the hearing aid actually helps them to recognize sounds and also to be able to speak better in the future. Okay, but this one, and this is an important one. Okay, this is ultrasound. Okay, how is it? Okay, how is it that when we have an ultrasound, we can see the picture of the baby in the womb? Okay, and this is a very important application. Okay, get ready to copy lah. So the function of the transmitter P, okay, over here. So there are two components to this lah. Okay, there's a transmitter and a detector. Whereas, okay, tapi kan nowadays the thing that she's holding is both the transmitter and also the detector. Okay, but when the ultrasound technology first started, there were actually two things lah. One is a transmitter and one is a detector. But technology is now so advanced that they're able to combine both into one. And nowadays, even more advanced. We don't see this picture anymore. Nowadays, we see 3D pictures. So we are able to get a better. Picture of what the baby looks like, whether there's any deformities when the fetus is in the mother's womb. Okay, so ultrasound technology has already developed so much since then. But the working principle is still the same. There is a transmitter inside there which transmits ultrasonic waves. Remember, ultrasonic wave is more than 20 kilohertz. So when it transmits the waves, we cannot hear it. We can't hear it. So we feel like, what's happening? But actually what it's doing is transmitting ultrasonic waves. Okay. Now, so the waves are going to be transmitted over here. So wave kena hantar, and because it hits a reflector, which is the fetus, it's going to be reflected. Okay, and it will be reflected back towards the detector. So the receiver the function is to receive the reflected ultrasonic wave. Okay, so transmit, receive, transmit, receive. Okay, and so from the receiver, let's talk about how the fetus is scanned until an image is formed. Okay, these 4 points are important. The first one, we spread the gel into the mother's abdomen, okay, over here. Secondly, we have a transmitter that emits ultrasonic waves. Okay, the waves travel through the skin and are focused on the fetus. So the waves are not just, kena hantar dan kena sebar pergi entah ke mana lah. Okay, it is actually focused on the fetus. Okay, and so the ultrasound will bounce off okay, the dense surface such as bones and tissues, and they are received by the receiver. Okay, so the ultrasound is reflected, okay, from surfaces such as bones and tissues. That's why when you do when new mothers when they go for, you should ask your mom. You should ask your mom, how many weeks were you pregnant? Then only you did your first scan. Nobody does the first scan the moment they find out that they're pregnant. Okay, why? Because there's nothing to reflect on. Okay, it may not even have become a fetus yet. Okay, it needs to have a little bit of bones and a little bit of tissue. Enough tissue. Okay, the cells need to develop until there's enough tissue so that the ultrasound can, this one. So if let's say you're 1-2 weeks pregnant and then you want to go for an ultrasound, the doctor say you crazy, there's nothing to see there yet because it's all just cells only. Okay, so the ultrasound needs a little bit more, a little bit more substance lah. Then only you can this one. So go and ask your mom, when she was pregnant with you, how many weeks was she pregnant? Then only she got the first ultrasound, when they finally saw the first picture of you. Okay, nowadays, new mothers, they tend to like to keep the ultrasound and then they like to post on Facebook, oh, welcome, new member of the family. Okay, but go and ask your parents or if you have a sibling that just got pregnant, right? Ask how many weeks, then you went for ultrasound. And you will find that it needs to be a few weeks one. Okay, cannot be immediately after the positive pregnancy, then just go and ultrasound, cannot. Because must have bones and tissues for the ultrasound to reflect on. Okay, then there's a computer over here that analyzes the signal and forms an image on the monitor screen. So the basic one is this okay, reflect, the wave kena hantar oleh transmitter, dia kena reflect oleh the fetus back to the detector. Detector sends the waves into the computer and the computer analyzes the signal to form an image. Okay, why do we use ultrasonic and not X-ray? Actually, if you take a look at this picture, it looks like an X-ray picture, right? Now, why do we use ultrasonic waves and not X-ray? And this is very important, okay? Long periods of exposure to high-frequency radiation from X-ray can cause mutation in cell. Okay, actually, every time you do an X-ray, I'm not saying, okay, I'm not an anti-X-ray person, okay? I'm just saying that somebody who goes through an X-ray is not something that, okay lah, kau pergi X-ray dulu lah. It's not something that is taken very lightly lah. Okay, you have to consider many things before you can actually take an X-ray. Okay, you have to consider your health, whether your cells are healthy enough to be able to go through an X-ray. Because what X-ray does, okay, it disturbs the cells lah. Okay, but if you keep doing an X-ray or if you keep doing an X-ray for a long time, what is going to happen is your cells are going to mutate. I'm not saying this so that after this, oh, okay, Sir Marcus said this, so I don't X-ray after this. No, come on. Okay, the key word is long periods. Okay, maybe half an hour in the X-ray room, that's not a very good thing lah. Okay, because that can cause mutations in cells. Because you're constantly being exposed to the X-ray. That's not good for you. Okay, and this may cause abnormalities in newborn babies. Okay, so X-ray, X-ray, because of its high frequency radiation, okay, it can cause mutation in cell. That's why we prefer to use ultrasonic wave. Of course, if you have an X-ray, we can also get the same picture, okay, but it's dangerous for the baby. Okay, so unless we really need to, okay, unless the doctors really feel that, okay, we really need to do an X-ray, okay, they will usually try to avoid doing the X-ray. They try to look at the ultrasound a lot more. Okay, so let's be very grateful for the wisdom of our doctors. Okay, here's another video.
The heart of most ultrasound systems is a device called a transducer, which uses an array of piezoelectric crystals. A piezoelectric crystal vibrates when an electric signal is applied, producing high-frequency sound pressure waves, which we call ultrasound. More importantly, this type of crystal can also work in reverse. It can produce electrical signals when it detects high-frequency sound pressure waves. When a transducer directs ultrasound waves into the body, they pass right through the skin and into the internal anatomy. As the waves encounter tissues with different characteristics and densities, they produce echoes that reflect back to the piezoelectric crystal. This happens more than 1,000 times a second. Returning echoes are converted to electric signals, which a computer converts into points of brightness on the image, corresponding to the anatomic position and the strength of the reflecting echoes. A medical transducer contains a large array of crystals, which allow it to make a series of image lines that, together, form a complete image frame, called a sonogram. In addition, all the crystals are repeatedly activated many times in such a way that a complete image frame is formed around 20 times per second, so that real-time motion is displayed in the ultrasound image.
Okay, wow, 60 seconds of science. Anyway, it's pretty interesting that technology has developed so that we not only see the picture of the fetus in the womb as a frozen picture, but we can also see it moving in real time. So that's how doctors use it to detect whether there's a heartbeat, okay, whether there's any abnormalities in the organs. Okay, it takes a lot of skill, to read that picture. Okay, to read this picture, okay, especially at the beginning stages. Now we can see, okay, very clear, this is the head, it looks like the hand. I'm not sure what this is. I think it looks like the hand, okay? But it takes, it takes a lot of skill, okay? It takes a lot of skill to be able to read it, especially when the baby is still forming. Okay, so let's be grateful to our doctors. All right, another application of waves is what we call a parabolic dish. Okay, so the word parabolic comes from two words, parallel and bowl. Oh, bowl, sorry, not bone. Okay, parallel bowl. So a basic parabola, okay, is a shape of a bowl. And then after that, it's a little bit and then there are two parallel lines. So a very normal parabolic shape is a wine glass. Okay, sorry if you don't drink wine, then ignore me lah. But if you've seen a wine glass is the shape of a parabola. Okay, and then and that's why I don't know if we have done this, but I may do this on Friday lah. You know the one where you dip your finger in water and then you woo, 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 that one okay, it can only work with certain kind of glasses, and the most important shape is that it must be a parabolic glass lah. Okay, you cannot use it on your mug lah, tak boleh, because it's not parabolic enough. Okay, and because parabolic dishes like this one, your astro antenna, okay, uses reflection in satellite communication. So radio waves from communication satellites are reflected by the parabolic dish, okay, and are focused to the antenna of the feed horn. So what happens is you have all these signals coming over here, okay, all the signals coming over here, and because of the shape of the parabola, it's all going to be reflected onto this receiver. Okay, they are all going to focus. Okay, all the signals will be reflected and focused, okay, onto the antenna. Same thing like our astro. Okay, the astro, the signal come here, the signal come here, the signal come here. No matter where the signal lands, it's going to end up here. It's going to be reflected onto the receiver. Okay, so that's the function of that parabolic dish, to reflect the radio waves onto a specific place so that we get a strong signal. Okay, that's the second one. Okay, third one is oil and gas exploration. Okay, have you ever wondered how do people know that down there got oil and gas? Okay, you mean they dig, they just, tembak saja they dig? No lah, okay. Takkanlah you want to dig several kilometers under the surface of the earth, and then what if you gagal? Terus, oh, okay, sorry, my bad. Okay, so what they do is this. The patterns of reflected sound waves caused by different rocks enable the location, depth, and structure of the seabed, which contains sources of natural gas to be identified. Okay, so they use this thing called the geophone. Okay, so they place it at different places, and then they have and then they kind of make an explosion, okay, so that the entire ground shakes. And so what happens is that because of this explosion, the waves are going to be reflected back onto these different geophones. Okay, and so because of that, the geophones are able to tell us, oh, okay, there is oil and gas, okay, because of the different structure. Okay, so the use of the geophones and reflection helps us to determine whether there is oil and gas over at that place or not. Okay, so bukan diorang main sembarangan korek-korek saja and then, okay, sorry, gagal. Tiada, no such thing. Okay, in the deep sea also this happens. Ultrasonic waves is transmitted to the seabed and it is reflected by the receiver. Okay, so instead of using geophones, which is on the land, they use hydrophones, which is in the sea. Okay, so again, if you have ever seen the oil rig in the sea, how did they know that there's oil over there? Okay, they use this thing called hydrophones. So geophones and hydrophones, okay, have really helped us to determine where there is oil and gas deposits. Okay, now one of the most important, if not the most important, okay, is this thing called the sonar system. Okay, so what is a sonar? Sonar is a reflected ultrasonic wave. Actually, sonar is short form for sound navigation sound navigation radar. Okay, sonar. Okay, so sonar is sound navigation radar. I think navigation or navigating okay, I can't really remember, but it uses the same concept. It sends out ultrasonic waves, okay, and is used to navigate, communicate with, or detect objects under the surface of the water. Okay, so that the ship doesn't crash into them or have the second Titanic happen . Okay, so state the sound wave phenomena to measure the depth of the seabed, it will be reflection, definitely reflection . Okay, now explain why sonar using a high frequency is used. We use ultrasonic waves, which is high frequency. Remember, ultrasonic is beyond 20,000 hertz. So why do we use 20,000 hertz? Because high frequency means high energy. High energy means can move further. Because when you send out the waves, the wave have to overcome all this water friction, there's all this water there that is going to stop the waves from moving. Okay, so we have to send it at high frequency so that it has high enough energy to enable it to move a lot further. Okay, now this next explanation is probably the most important one now of all the applications. This is, if it is in the exam, this is the one that's most commonly asked. Okay, how do people measure the seabed? Same like the ultrasound just now. You send out a wave, you wait for it to return, and then after that you use a computer to analyze. Okay, so same thing. A transmitter emits an ultrasonic wave. Okay, again, the key word is ultrasonic wave. The ultrasonic wave is reflected by the receiver. Okay, sorry, reflected by the is. Okay, sorry. The ultrasonic wave is reflected and, okay, sorry, this should be and is detected by a receiver. sorry for the English. Okay, then because there is some time taken over here, right? Okay, so there is a time interval for the ultrasonic wave to propagate to and from the seabed. So we measure it. Remember just now in the case of the trumpeter, okay, the woman just now blowing the trumpet. So she blow, and then after that, a few seconds later only, the wave comes back to her. Actually, not a few seconds, like a few milliseconds later. So there is a time interval. Ada masa untuk dia pergi dan kembali. Okay, so we need to measure that time interval. And so we use that time interval and this formula, S equals to VT over 2, to measure the depth of the seabed. And that's how people know how deep the sea is. Okay, they use ultrasonic wave okay, and then they count the time where they send out, and then the wave comes back to them, okay, and then they use this equation, S equals to VT over 2. Actually, not S lah. Most people like to use the word D for depth, okay, to calculate the depth of the seabed. Of course, V is the speed of the ultrasonic wave. Okay, this one usually is given lah. Either given or you have to calculate. Okay, but V is, can be calculated. Okay, so I want you to take a note. One formula is this, D equals to VT over 2. But at the same time, remember the original V formula. Okay, V equals to F lambda. Okay, so we can substitute this F lambda into here, okay, to get D equals to F lambda T over 2. So this one also is possible. This one also is possible, depending on what is the information given to you. Okay. All right, let's take a look at a couple of problems involving this one. So this one, time taken is 0.28. Okay, and then the speed of the sound is 1,500. Can you calculate the depth of the seabed, please? S equals to VT over 2. Okay, do it now. Do it now, and then I would like let me see. What happened to Steffi? I haven't seen Steffi for the longest time. Okay, well, okay, I want Elvin to give me the answer to this question, please. Calculate this and tell me what is the answer for E. Just, yeah, how much is this one? 210. Okay, good. 210 meters lah, because depth of the seabed. Okay, so the formula is pretty easy to use. Okay, you just have to remember it lah, VT over 2. Okay, velocity times time, then you divide it by 2. Why do we have to divide it by 2? It's because the sound waves go and then come back. Okay, so that's why we divide it by 2. Now, explain why the speed of sound in water is higher than the speed of sound in the air. Okay, because water molecules are closer and sound energy can be transferred faster. And this is true, We don't think about this because we always think that when we shout inside the water, we cannot hear the person inside the water, which is true. Okay, you cannot hear, but that doesn't mean that the sound speed is slower, This is something that a lot of people cannot seem to get past, because they think that if you can hear the sound, means the sound is faster. Okay, and I have said this in the first subtopic until now, Sound moves faster in solid, then in liquid, and then in the air. It's just that we are so used to the air, that we always think that the speed of sound is faster in the air, when it is actually not true. The speed of sound is fastest in the solid, because the solid molecules are very near to one another. But it is difficult. Okay, it is difficult to hear. That one I know. Okay, because you yeah. Okay, because in solid, you want to put your ear into the wood or into the rock. Okay, but in the water also it's true. The speed of sound in water is much faster than the speed of sound in the air. Okay, because remember, sound waves are transferred by compression and rarefaction. Okay, and because the molecules of the air are much further apart, it is more difficult. It is slower, okay, for them to transfer the sound waves over. Okay, so we need to unlearn what we thought we know, okay. Sound travels faster in water, although it is more difficult for us to hear somebody shouting in the water. I'm not saying that if you talk, hey, how are you, in the water, means you're going to be able to hear that person. Totally nothing to do. Okay, totally nothing to do with whether you can hear or not. It's just that the waves travel faster. That's it. Wave travel faster doesn't mean that you can hear. It just means that the wave travel faster only. Okay, so be very careful about this. All right, let's take a look at a few more problems. 3 more problems, and then we're going to call it a day. So ultrasonic waves of frequency yada yada is transmitted from a ship to a seabed to determine the depth of the sea. Wave speed is 1,500. Ultrasonic wave is 25 kilohertz. Okay, the time interval between transmission and the receiving back of the ultrasonic is 120 milliseconds. Okay, be very careful about this. Okay, milliseconds means you have to change 120 times 10 to the power of negative 3. Okay, we have to do this in seconds. 25 kilohertz means 25 times 10 to the power of 3 hertz. Okay, be very careful about it. So kilo is 10 to the power 3, milli is 10 to the power negative 3. Okay, so question A, Bernardine, can you determine the depth of the sea, please? Same formula, Vt over 2. And then after that, Carlson, wavelength. Okay, sorry, the wavelength is V equals to F lambda. Okay, we want to count the lambda. Can you quickly count this, please? It's 90 meters. How can it be 90,000 meters? Ow. Okay, guys, be careful of this. Okay, when you see ms is milliseconds and kHz is kilohertz, you need to change it into SI form. Okay, Carlson, the next one, please. What is the wavelength of the ultrasonic waves? We have V, we have F. Okay, we have V. Yeah, we have V, we have V, we have F. Can you calculate the lambda, please? So the V equals 0.06 meters, okay, which is about 6 centimeters. That's pretty normal. Okay, so 1,500 divided by 25,000, okay, V over F. Okay, so we get 0.06 meters. Okay, Carlson, are you there? Wake up. Okay, Carlson went to the toilet for a very long time. Okay, question number 3. Or number 2, whatever. Ahmad shouts in front of a high wall. He hears the sound of the echo 1.2 seconds later. This is the same as the trumpeter just now. Okay. The speed of sound in the air is 340 meters per second. Oh, sorry. Hold on. Okay, take a look at this. Speed in water is 1,500. Speed of the sound is only 340 in the air. Okay. Which is what I said just now. The speed of sound in water is much faster. You may not be able to hear it, but it's definitely true that the speed moves faster in water. Okay, again, what is the distance between Ahmad and the wall? Same thing. Chloe, can you count this, please? S equals to Vt over 2. I don't think there's anything to change here. Okay, but we use the same situation to calculate the distance between Ahmad and the wall. All right, good. 204 meters. Very easily counted. 340 times 1.2. And then you get 204 meters. So in this question, it is pretty much the same as the ultrasonic one, okay, except that, oh, sorry. Okay, except that there's no changing of millisecond to second or kilohertz to hertz. Like everything is given normally. Okay, one last one. Radar, same thing, same thing as the one with the sonar. Okay, so you have an airplane and you have a control tower. So a radar transmits a signal to an aeroplane. Ta-da! Okay, the velocity of the signal is 3 times 10 to the power of 8 meters per second. Okay, now after 4 times 10 to the power of negative 3 seconds, so all the units are pretty set, the radar detects the reflected signal. What is the distance? Again, okay, S equals to Vt over 2. Can I have Vivian for this, please? Careful, okay, careful with all this 10 to the power of negative 3. Make sure you calculate properly. Everybody also calculate, but I want Vivian to give me the answer for this. All right, 600,000 meters, which is 600 kilometers away. Okay, very far. Okay, that's why the velocity of the signal is very, very high, 3 times 10 to the power 8. Okay, so the velocity of the signal is very high, 3 times 10 to the power 8, so that it can go very far. Okay, we need it to go very far because as it travels, it's going to lose a lot of energy. Okay, so it will be like just nice for it to come back and we can detect the timing. But you see, 600 kilometers, right? But the time that it detects is 0.004, 123 seconds. Okay, do you notice how amazing this is? The plane is 600 kilometers away, but the signal sent out and come back in less than 1 second. Okay, that's how amazing reflection technology is. Right?